luncheon of the spring semester. So believe it or not, we are heading towards the spring. We just went through a very difficult winter break. Whoever stayed around here, it was freezing, and we went out of the habitable zone around the sun.
Let me interrupt. Avi usually spends that time in Israel.
Well, I'm just defining the habitable zone based on the rules of astrobiology. Biased in any way. But we are back to the habitability, as you can tell, and we are here to listen to 4 exciting presentations. And we just heard an excellent ITC colloquium by Eric Peng over there, and he comes to visit us from Peking University. Although, the way you presented things looked extremely American to me.
Well, I am a New Yorker.
That's exactly. So one could tell. So we'll start with Morgan MacLeod, who will tell us about the Runaway, Coalescence, the onset of common envelope episodes. And then we'll hear from Yamila Miguel from Leiden Observatory, who will speak later today at the CFA colloquium. Is Yamila here?
Yeah.
Oh, okay. And she will talk here about the detectability of sulfur and phosphorus species in exoplanet atmospheres with JWST. We all hope that JWST will fly in mid-2019, but it's being postponed to the point where the decadal survey will not depend on it anymore. That was the decision made 3 months ago. And then we'll hear from Eric again. He will talk about the global cluster systems of ultra-diffuse galaxies. And finally, we'll hear from Dan Dorazio, who will discuss imaging the orbits of massive black hole binaries. Morgan.
Thank you so much, and I'm going to do my, as you can hear, my voice might or might not last for the duration of this, even though it's only 10 minutes, I promise. But I'll do my utmost not to cough into the microphone. Okay, so today I want to talk about common envelope episodes, and in particular, things we're learning about the very beginning of those episodes. So today won't be about the whole story, but just the onset of these interactions in binary star systems. So first, what are these and why do we care? So to form a pair of compact objects that can merge under the influence of gravitational radiation, we actually need some phase of orbital transformation in that binary system. So if you put 2 neutron stars separated by about a solar radius, they'll merge in the lifetime of the universe. But wider than that, and they won't. And so you can imagine that that separation doesn't accommodate even the main sequence radii of the massive stars, which need to evolve and leave behind neutron stars as remnants. So we need some process which transforms the orbit of these binary systems. One possibility is a phase of binary interaction which we call a common envelope phase. And this is a cartoon version of it, but the basic story is that one star evolves to the giant branch and engulfs its companion, and then sort of like a satellite entering into the atmosphere, the 2 stars get dragged closer and closer together through interaction with that gas. And finally, if this process is to be successful, the binary has to be sort of a dramatic enough egg beater in the center of that gas to clear out its surroundings, stabilize, and leave behind a system that's been transformed by this process. Something that we actually missed in this cartoon picture that we've learned sort of observationally is that there's another phase here, and that's that this process of one star getting sort of engulfed by another is not gentle, but in fact leads to shock heating and mass ejection that powers optical and infrared transients that have been observed in time domain surveys. So I want to focus on those transients today and what we're learning from them. The emission that we see is powered by just cooling of this freely expanding gas that's been ejected. And so these are objects that get redder as they fade because the temperature is going down as the material expands. A particularly sort of telling transient that defined this category, I think, was a galactic transient V1329 Scorpius. So this was an object that had a 10 magnitude flare. And folks looked backwards in time. It happened to be in the Ogle field, and they saw an eclipsing binary with a decreasing orbital period. What made this remarkable was on the other side of the flare, they only saw a single object. So this was pretty clearly a merger of a binary star system. Recently, we've discovered a few of these in local galaxies, and those I think have been especially useful. So let's turn our attention to the Andromeda Galaxy and a transient in January 2015. This object, which you can see right there, the red marks, is exciting, I think, because we know the distance to M31, and also because there's incredible archival imaging of these local group galaxies. And if we look at the location of this outburst, HST sees something like a subgiant branch, several solar mass, maybe 30 or 35 solar radius star prior to the outburst. I think where this becomes really interesting is when we compare it to the light curve that that star produced, presumably through interaction with its unseen companion. So here's that light curve in a few bands, and the only feature I want you to notice here is that the time scale of rise to peak, from discovery to peak of this light curve, is similar to the orbital period of a test mass around the surface of that pre-outburst giant star. So I think this is kind of interesting because we have a binary system which has survived for approximately eons, its main sequence lifetime, and all of a sudden in one orbital period it goes terribly wrong. So that's sort of troubling to understand at face value. And I think it's particularly confusing in light of the next piece of evidence that I'll show you, which is I'm switching objects on you because this one has better data, but this feature is universal. All of these sources seem to show some extended tens to hundreds of orbits of what I'll call precursor emissions, some gentle brightening leading into this major outburst. So the question I want to ask for the rest of the talk is how can we reconcile something which seems so impulsive with this kind of extended lead-in? If we just saw the impulsive signature, maybe we would think that this isn't actually an impulsive process, like a direct collision between two stars. But that doesn't seem to be the case. So the approach that I've taken to understanding this is to simulate the gas dynamics of this interaction. So I'm going to show you mass transfer from a more massive donor star onto a less massive accreting star marked with a little symbol there. And what you'll see is that material is being pulled off from the donor star. It's settling around this accreting star, but it's sort of piling up faster than it can accrete, and so material is being trailed off through the outer Lagrange points of the binary system. We're obviously in a frame here where we're flying along with the rotation, otherwise you'd be completely dizzy. So you might be noticing that now we're actually coming closer and closer together, and in these last moments, the shrinking of the orbital separation really runs away to accelerating rates. And looking at the path of the orbit in the frame that's centered on that donor star, we see it starts as this tightly wound spiral and ends up with really kind of this loose plunging together of the two stars. In terms of the orbital separation, we see that it takes a long time for the orbit to decay near the initial separation where mass transfer starts, and then it really accelerates so that by the time the separation is similar to the size of the stars, they're actually plunging together quite rapidly. Another way to look at this is in terms of the number of orbits over which the orbit is decaying. So this is the ratio of the orbital decay timescale to the orbital period. And starts out more than hundreds and declines to tens, and by the time the separation is similar to the size of the object, over one orbit, the orbital separation is changing by a bordering unity. So that's sort of the qualitative picture, and something else you may have noticed is that the morphology of this flow changes hugely. So we go from this a thin stream of material crossing in the system with a little bit sort of percolating out of the outer Lagrange points to this really kind of massive outflow that has this broad fan and is incredibly mass-rich by comparison to the early interaction. And I guess I'll suggest, although this is sort of early on, that we might associate the outburst itself with this runaway plunge together and the associating ejecta, and the precursor with this long-term interaction which eventually runs away into the sort of accelerating state. So that's sort of the what happens, and I want to give you a sort of hint at the why. So here I've quantified something to do with the exchange of angular momentum in the system, and that's the density of torque in a slice through the orbital plane. So as we watch this, pink material is material that's pulling the two stellar cores backward in their orbit. And green material is pulling forwards. If they're perfectly in balance, the orbit just goes on and does its thing. There's no net torque. So you have to sort of integrate by eye. And as you do that, you might notice that there's some asymmetry there. And that asymmetry is what's driving the evolution of the orbit. And as these two come closer together, you'll see deeper colors. So more mass, basically, per unit volume involved in driving the torques. And you also see increased asymmetry there. And both of those things contribute to this runaway that we're seeing. So in closing, I think we're learning that transient outbursts in the optical and also maybe in the infrared are actually tracing these phases of binary interaction that we've wanted to know more about for a long time. These phases are critical to the formation of compact binaries, and they've been, I think, theoretical uncertainties for quite some time. And through modeling the associated sort of gas dynamics and eventually the light curves, we want to constrain what's going on here with the help of that empirical information. Thanks so much. So what's really interesting is early on, so this is, we're modeling the gas dynamics. It's hydrodynamics, not MHD. So we're not modeling the magnetic field. So I can't comment on that yet. Early on, the pressure is really important. And basically, it's pressure gradients that's pushing some material into those streams that outflow from the system. Later on, where you see that fan of ejecta, when I overplot just free particle trajectories, they exactly follow the streamline. So the late interaction really is not even gas dynamics, but just sort of ballistics in the co-rotating potential, which is kind of fascinating transition.
Well, it's a very nice and clean approach to a really complex question. So in that sense, I think it's very beautiful. Let me ask you, how does this depend on the star? Or in other words, you might have a main sequence star of low mass, a supergiant, any in that range.
Yeah.
So what does your simulation apply to, and how do you anticipate it would be different for different stars?
Yeah, so the particulars of this simulation, one star is a giant, so it has some mass concentrated in the core and extended envelope. And then
Have a wind already before this starts?
it does, although I start it when it's already sort of directly transferring mass.
Okay.
And the other object is some more compact companion, a main sequence star or something else that's not really resolved. We're just resolving its gravitational interaction. So I think in my sort of tests, I think the structure of that donor star is somewhat secondary to the sort of overall mass ratio and interaction, but there's more to be done there, and we don't completely know.
Do you think that feedback from the accretion luminosity of the companion could be important?
It might be, and it's just something that folks haven't looked at in a lot of detail yet. I think especially in that early phase where you're sort of forming an accretion disk, there would be accretion luminosity sort of escaping. It's not clear that it dynamically does that much because it would have to kind of impinge on the stellar interior material, which is causing the drag forces that pull the orbit together. So I don't know what it would take for that luminosity to be dynamically important versus sort of important in the appearance. So interestingly, in some of these cases, actually the flow, if it were a compact object, easily exceeds the Eddington limit because photons are basically completely trapped and advected with the flow. And the densities we're talking about are stellar interior densities, which are huge by comparison to most accretion flows that we think about. Yeah, Dan.
Yeah, so the kind of sharp increase in torque on the binary,
Yeah.
you said it was caused by this change in the flow from the stream to kind of a fanning.
Yeah.
Is this simply being caused by the L1 tunnel point being pushed inside the star, or do you ever?
Yeah, no, it's actually caused by the star initially is locked into tidal co-rotation with the orbit. And as the orbit shrinks, the star doesn't spin up. The angular momentum goes into the ejecta. And so by the time the orbit has tightened, the orbital frequency is much higher than the star's spin frequency. So you go from a configuration where sort of you have this thin stream of mass transfer to a configuration where the smaller star is racing around the surface of the big one. And that sort of gravitationally slingshots material out in that fan.
The stellar spin will change exactly when this happens.
Yeah, so it has to do with that sort of loss of co-rotation or the desynchronization of the orbit and the stellar spin, I think. Yeah. Thanks so much.
Yes, because then I can, okay. Thank you. Maybe here is better. Okay, so hello everyone, bon appetit. So I'm Yamila Miguel. I recently moved to Leiden Observatory like 3 weeks ago. And today I will be giving the colloquium also this afternoon on a different topic actually. But today I wanted to show you some of the work that we've been doing studying the chemistry of sulfur and phosphorus in exoplanet atmospheres and its potential detection with JWST whenever it's up there. So first, why to study the atmospheres of these planets? So giant planets are very interesting objects. They are the first ones to form in a planetary system. So understanding their atmospheres and their interiors really are key to understand the formation of those systems. So we want to understand them better. We want to understand the atmospheres of these exoplanets and also compare them to the planets in the solar system as well. So one question that we always have when modeling these atmospheres is if we are considering all the relevant chemistry. And this is important because if we are neglecting some important chemicals, this might affect other very abundant chemicals in the atmosphere, and we might be misinterpreting the observations that we are getting because we are miscalculating the abundances. So we really need to know which are the most important chemicals and try not to neglect others. So in the case for this work, the motivation, like the question is why to study sulfur and phosphorus? And the thing is that if you look at Jupiter and Saturn, those species were detected
in those not exo, but in those planets. And we wanted to know if they are important in exoplanets as well. Of course, the temperatures are much different. The exoplanets are very, very hot compared to Jupiter and Saturn. And the chemistry changes a lot when you go from a cold planet to a very hot one. So we wanted to know what happened in those cases. So this is very simplified scheme showing the model that we are using. So these are the input parameters, the stellar data, the planetary data, the thermal profile of the atmosphere, and we need to say something about the elemental abundances of the atmosphere. And in the case of this study, that, by the way, I didn't say it, but I've been doing this with Dong Wang, which was, at that point, a PhD student at Cornell University. He just finished, and Jonathan Lunin. So what we did was to take solar composition as a starting point. Of course, there is no reason to believe that the exoplanets will have solar composition in their atmospheres, but it's a starting point, and we want, of course, to change this in the future to see how different elemental abundances at the beginning will change our results. So we performed the chemical calculations, and for that we were considering disequilibrium chemistry, not only equilibrium. So, but we don't have photochemistry, so we were considering mostly the effect of the vertical mixing in the atmospheres. And we have like a very big reaction list of more than 1,500 reactions or so. And the new thing is that we included like 200 reactions for phosphorus that hadn't been explored in the context of hydrogen-rich atmospheres before. So after getting the abundances in the atmosphere, we calculated the synthetic spectrum, and finally we applied JWST noise model to see if it was possible to detect those species or not. So talking about the chemistry first, we were studying planets between 500 and 2,000 Kelvin. And here what I'm showing is the molar fluxions and for different temperatures, and different colors represent different species. So these are all at 1 bar. So for example, here we have water, this blue line here, which is very abundant. Then we have this other green one here, which is methane, that you see it's abundant for hot planets, and then, for cold planets. And then it's not so abundant when we go to hot ones. We have this other species, which is NH3, that is similar the behavior as methane. This is N2, and this black one here is H2S, which is the primary carrier of sulfur for all the temperatures that we've been studying. So it's actually very abundant, and we definitely need to take it into account in the chemical calculations included in the retrieval codes as well. And it's also very abundant in all the temperatures. We have other species, so this one here is pH3, which is the primary carrier of phosphorus for actually cold planets, for planets with temperatures lower than 1,000 Kelvin. So when we go to hotter temperatures, pH3 gets dissociated, and then the primary carrier is pH2, which is not really abundant and not so interesting for this study. So that's why we kept only the cold planets, let's say, with pH3. But you can see that it's quite abundant, like compare, for example, with CO2, which is this one here. So pH3 is more abundant, up to planets of 1,500 Kelvin. So these are really important species, even for hot exoplanets. So for the spectrum, we modeled the primary and secondary transit. And here we have in red, in blue, when we use all the species, and in red, when you excluded the pH3 in this case. So we detected this feature at approximately 4.1 microns. That is very visible here in the primary, but also in the secondary transit. And this is for the planet of 500 Kelvin. So it's a relatively cool planet. The thing is that if we go to higher temperatures, then we don't really observe that feature anymore. There are other species that are more abundant and really are the ones determining the spectrum. For the case of sulfur, it's the opposite. So we really need to go to high temperatures to observe H2S. So when we are at lower temperatures, we cannot observe it. Again, there are other species that are more abundant. But when we go to these hotter temperatures, then we can observe, and we detected these two features. One is this one here at approximately 2.8 microns, and this other one here at 3.8 microns. And we can detect it in both, again, the primary and the secondary transit. So the question now was, okay, is this really detectable with JWST? So we put this spectrum in the noise model for the JWST, and what we found, you can see it here. So this is the case of the phosphorus pH 3, and you can see that it's, we can actually observe it. It's approximately 40 ppm. This one is a bit lower on the secondary transit, it's 20 ppm, but the sulfur is even more interesting, also because the planet is hotter. So for this case, here we have a signal of 100 ppm, and in both cases, in the primary and in the secondary transit. So these are very important species. We definitely need to take them into account. So here we studied planets between 500 and 2000 Kelvin, and we determine which are the most important species, especially for phosphorus at those different temperatures. This one is definitely the one that we have to be looking at. And for sulfur, we have H2S, which is the primary carrier for all the temperatures that we've been studying. And, well, as I said, they are important species. We cannot really neglect them anymore in our chemical networks. And we detected these different spectral features for phosphorus at 4.5 microns approximately, and two other for H2S. So I hope that we will be hearing more about this in the future. Thank you. Yeah, it depends on the temperature. So we study the chemistry depending on the temperature, yes. Yeah, because this really doesn't depend on, so it depends on the temperature, definitely, and the elemental abundances that you have. So we apply this here to an exoplanet just to put an example, but these are important chemicals that we start to start looking at. Yeah.
Is H2S a dipolar molecule like water?
Oh, I'm not sure about that. Why are you asking?
Does it form clouds like water?
Oh. So in Jupiter, there are clouds, but not of that species. It combines with magnesium and it forms clouds. But we don't think that that could be the case in these very hot planets, because Jupiter is much colder. So that's why it was also another incentive to look at that molecule. But that's definitely something that we need to study more.
So you showed that both of these have impact on the spectrum, but I was wondering how degenerate it is with other species. So how well could you measure it in some kind of org modeling way of the spectrum?
So the reason why, so we tried in a very large wavelength range, and the one I showed there was the one that more relevant for these ones. So for example, if you look at a shorter wavelength, then there is molecules like water that have a much more impact, and then you cannot see the features of these species even if they are present. So it really depends on the wavelength. The one that I'm showing here are the best temperatures and wavelengths to look at these specific species.
Later today, we will hear from Yamila about the results from Juno.
Oh yeah, it's super exciting.
Very exciting, especially because also a member of the team is our Dean of Science that is about to leave this course this summer.
Oh.
Jeremy Gottsman, you probably know him.
Yeah.
So we had some personal investment.
Oh, it's really cool. I have cool pictures, I'm telling you. So, oh yes. Otherwise, everyone was going to hear me eating. I totally forgot that.
No, I do not want multi-port. Okay. Right. So it's a pleasure to be here and to be speaking again here. I will be telling you about some recent work that we've been doing on globular cluster systems in ultra-diffuse galaxies. It's not published yet, but from what I hear, more people will be watching this talk than will ever read our paper. So I guess this is it. This is just as introduction, an idea, give you a picture of what an ultra-diffuse galaxy is. This is a term that's come into the literature very recently, the past few years, and you've probably heard a bit about it here. This is a picture of what's been dubbed an UDG, ultra-diffuse galaxy in the Coma cluster. And what's circled here are objects that are likely globular star clusters associated with it. And to give you an idea of why these things are interesting, down here we have another galaxy which is much more sort of normal. It has a normal size for its luminosity, but these two galaxies roughly have the same stellar mass. So you can see that this galaxy here is much more diffuse, is larger, and some of the largest cases have sizes that are comparable to that of the Milky Way disk, but having luminosities or many, many magnitudes fainter. So this is a very low surface brightness system, yet kind of mystery here is why something that has such a low density in stellar mass can still form these massive star clusters. And so what are ultra-diffuse galaxies? If there's one thing that's ultra about them besides being diffuse is that there's an ultra large number of papers being published about them over the past 2 years or so. But actually, this is not a recent phenomenon. I just wanted to point out. This is a galaxy that Nelson Caldwell, who's here, published in 2006 in the Virgo cluster. And if it were to be, if it was discovered today, it would be called, an ultra-diffuse galaxy, right? This is a galaxy that has a size of about 2 kiloparsecs, but has maybe stellar mass, luminosity of minus 15 in V and absolute magnitude, or about 10 to the 8th solar masses. And so what's very interesting about these is that it seems like at least some of them might be extremely dark matter dominated, right? So depending on how you're measuring, whether through stellar kinematics or maybe through just the number of globular clusters that you're counting, the mass to light ratios that we're talking about are really, really high, right? Like 1,000 or more. And that has given people the idea that maybe these are, failed galaxies, right? Galaxies that just, like Milky Way mass galaxies that got started and somehow never finished the way the Milky Way did. So one of the most extreme examples is this galaxy DF44, DF being for the Dragonfly camera that was initiated by Peter Van Dokkum and Bob Abraham. This very low surface brightness optimized imaging camera array of telephoto lenses that discovered a number of these objects in the Coma cluster. So dynamical measurements, that was a stellar dynamical measurement, and other dynamical measurements using globular clusters. We had a paper on this galaxy I was showing you in the first slide, DF17, where we speculated that maybe these galaxies are failed in the sense that they're pure stellar halos. So if you look back to this image here, this is actually this would be the halo of M33, roughly speaking, in size, luminosity, number of globular clusters, if you just took M33's disk out of the picture. So maybe we're forming stellar halos and just not forming the rest of the galaxy. So now we're increasingly knowing more and more about it. Some of the work's being done right here. This is a really nice paper by Mungu using the manga set of spectrographs on SDSS, where we actually can get spectra for these things that are really faint. We know that at least for a few of them, they are old, like as old as globular clusters, and they're metal poor. So they're like very old low surface brightness dwarf galaxies in that respect. And maybe they're related to the normal early type dwarf galaxies. So, Nicola and Avi here have published papers saying that maybe they're just the high angular momentum tail of the normal dwarf galaxy distribution, so they're just more extended. There are other ideas that maybe this expansion is due to feedback, so you have all this intense star formation in the center, and that redistributes the dark matter and the stars, and so that causes this diffuseness as well. Another popular idea is that there's sort of tidally stripped remnants. You start with a more massive galaxy, you strip out most of the stars, the size doesn't really change very much, and you end up with this diffuse core. Now, globular clusters can be a window onto this because they track the early and intense star formation in galaxies, and Nicola has a nice paper on some of these diffuse galaxies in coma and looking at their globular cluster systems. So I wanted to bring this to an HST survey that we're doing of coma cluster UDGs, and this complements the previous work that's been done because a lot of the archival data was just in the core of the coma cluster. We have an HST program where we've targeted 33 of these dragonfly identified galaxies that span a more representative range of the environment in coma. And what we've done is specifically, we have one filter to look for concentrations of what could be globular clusters in these galaxies, because we want to see how common is it for these massive star clusters to form in such diffuse galaxies, and maybe what does that tell us about their masses and their progenitors. And so these observations were just finished last year, and all the galaxies we've targeted are sort of large, right? Larger than 2 kiloparsecs or so. And this has been done, being led by Sung-Soon Lim, a postdoc at the Kavli Institute in Beijing. Now, just looking at some of the images, here is a UDG in coma. These red circles are globular cluster candidates, so they're possible globular clusters. And some of these galaxies look like this. They don't seem to have much of an associated globular cluster population, but some of them look like this, where you can see much more of a concentration of these globular cluster candidates. And when we go across the whole sample, we can look at the number of globular clusters as a ratio with the stellar light. So that's a number called the specific frequency. And just remember that one globular cluster for an absolute V magnitude of minus 15 or 10 to the 8 solar masses is a specific frequency of 1, right? So here at MV minus 15, a specific frequency of 1 is one globular cluster. And so what we've done is not just look at the UDG population, but we've actually used our own data and archival data to come up with a relevant control sample. So that is all the kind of normal, or what we would call classical dwarf galaxies in the coma cluster, and to see what their globular cluster population looks like. And that's this blue curve. So on this plot, you have a lot of points, but the black points here are galaxies in the local universe. This blue curve, we didn't plot all the points, but this blue mean and then the shaded region show the sort of 1 sigma band of what kind of specific frequencies, so the number of globular clusters, again, per unit field star light, do you expect for classical dwarf galaxies in the coma cluster. These red points now, all the red points, whether filled or open, are what we've defined as UDGs, ultra-diffuse galaxies in coma. And the red line is the mean. And what seems to be the case is that in the mean, these galaxies seem to have more globular clusters than the typical dwarf galaxy of similar stellar mass. About half of them have these elevated numbers here, although there are quite a few here that have numbers that are indistinguishable from normal dwarfs, and some are consistent with 0. Another result out of this survey is that we can look for nuclear star clusters in these galaxies. A lot of typically early type dwarf galaxies can have nuclear star clusters, and in the coma cluster, you see a lot of these kinds of galaxies. For our sample, 6 out of 33 have an apparent nuclear star cluster, and we don't count the nuclear star cluster in the globular cluster counts. So the question is, like, how do these properties correlate, right? What is causing this elevation in globular cluster numbers? And it doesn't, surface brightness, shows some, we've defined the samples by surface brightness. So red here are UDGs, blue are normal dwarfs. And yes, they're slightly higher here. So looking for internal properties. External, you're looking at environment. So looking at radius from the center of coma, it's kind of hard to see any strong trends. Maybe there's something like the more elevated ones are at the center. Here what I'm showing is splitting the sample, the UDGs, into those with high specific frequency and those with low, and then looking at the ellipticity, B over A. So the blue histogram here is for low numbers of globular clusters, and the red is for high. And it looks like this, it's like a 2 sigma kind of effect where those with low numbers of globular clusters are more elongated, sort of more, and the ones with high numbers are round. But it seems like these globular cluster system properties are kind of weakly correlated with anything that we could think of plotting. Now, one thing that's been quite popular to do nowadays is to use the number of globular clusters as a proxy for the total halo mass, because it seems like they do trace each other. And so what we've done is plot, this is the halo mass that we've inferred using just a constant offset that's calibrated from local data. And if you want just observed numbers, this is the total number of globular clusters. And this is the stellar mass here. This is the stellar mass-halo mass relation, sort of what you'd expect. This blue region are normal galaxies. This is, again, the sort of elevated numbers for the UDGs, showing that, that you basically have a very low stellar mass fraction in these galaxies. Now, you want to get real masses, so we have a program to do that in the Virgo cluster being led by Elisa Toloba. We have some preliminary results in a paper showing that this is a mass-to-light ratio of galaxies from regular galaxies in the field, and this is sort of the sample of elevated mass-to-light ratios for these UDGs. So they're very intriguing. There are many different ways possibly to make them. There may be multiple formation channels. We don't have the answer yet, but we're going to keep looking. Thanks. Mm-hmm. Yes, so I was rushing through the last slide because I'd heard the beep, but thank you for bringing it up. So in the coma cluster, at the moment, those globular clusters are too faint to do kinematics. But in Virgo, which is 6 times closer, we can do that. And so we've identified a few ultra-diffuse galaxies here. These are just 3 of them, where we've identified globular clusters associated with them, and we're getting spectra, and we're measuring velocity dispersions for them. And that's where we're getting these 3 red points are our data. And this is a sample of normal, gas-poor galaxies. This is sort of a dwarf elliptical type galaxy, and our mass-to-light ratios are fairly elevated. This is preliminary. The error bars are large, but they're elevated at the moment for these kinds of galaxies.
What about things like the globular cluster luminosity function or the colors? Are they different in any interesting way?
So for the coma sample, we only have 1 filter, so we can't do colors. But in terms of the luminosity function, it's at least we can say for the bright end of the luminosity function that it looks, for the numbers that we have, it looks fairly normal. For DF17, which was the archival data that went deeper, it looked like the luminosity function might be sort of narrower than what you'd expect locally. But again, the numbers are pretty small. So I think the jury's still out on that.
That assures you that these likely are globular clusters associated with the UDG.
Mm-hmm. So there's it's at this moment it's just statistical, right? We're looking for concentrations of point sources around these galaxies. Now, the beauty of HST is that its resolution allows you to reject the most common contaminant, which is background galaxies. It resolves most background galaxies. So, we do have some contamination from intra-cluster globular clusters, the occasional background galaxy, but it's a pretty clean sample. So if we see that concentration around, we make the assumption it's associated.
Yeah, I can see certainly for some of the ones, they really do seem to be there in the image.
Yeah.
But some of the ones that are further out, I was just wondering how confident are you that these are part of the group?
Well, I think for the ones that are beyond a few effective radii, it's very hard to say because coma is also a dense environment, and we know there are intracluster globulars there. So all we can really do is say what's the excess above the background.
And of course, each galaxy has a tidal radius around it, radius from the cluster supersedes. So it might be worthwhile seeing all your globulars sitting inside this tidal radius.
Yeah, that's a good idea.
So I'm just curious, are all UDGs in clusters?
No, there have been increasing more surveys of them. People have found them in groups. And I think part of it is how you define it as well. The original UDG selection from the Dragonfly data was essentially lower surface brightness than Sloan, right, or something you would consider low surface brightness, and then they had a limit on size that was partly, I think, their PSF. So it's not necessarily the most physical definition. So people have been doing cuts and saying, oh, we find them everywhere, but I think it's just there may be different kinds of objects as well being seen.
Because it's surprised the UDGs went out pretty far in the normal dwarfs, and the UDGs went out further than the normal dwarfs did in radiance.
That's due to limitations. That's the data.
Okay.
So there's a lot more data in the central regions for the normal dwarfs, whereas we were targeting the UDGs out there. So yeah, that's not real.
All right. Let me grab, I think there's a pointer stick over here. Whoop, used to be. Here it is. All right. Thanks a lot. So today I want to talk about some work that I've done with Avi Loeb. And the upshot is that we think it may be possible to directly image the orbital path of massive black hole binaries at the centers of galactic nuclei. So I want to tell you about that now. But first, let me motivate why that should seem exciting. So the idea is you have two galaxies with massive black holes at the center, millions to billions of solar mass black holes at their center. And when they merge, the black holes will be dragged to the center of the new galaxy, where they'll form a binary via dynamical friction. And that binary, the massive black hole binary, if it can become close enough, it'll then be merged by gravitational radiation in a very loud burst of low-frequency gravity waves that we'll be able to detect in the near future. The issue here, and why there's been an issue called the final parsec problem that's existed over the last 40 years, is that dynamical friction can bring the two black holes so close to each other will they'll form a binary. But at about a 1 parsec separation, dynamical friction becomes inefficient, and there needs to be some other processes that will bring the binary close enough to of order a centiparsec or a tenth of a parsec, where gravitational radiation can do its job. And so there are a number of ideas on how you can shrink the binary past this final parsec via gas or different non-spherical distribution of stars. And what actually happens there is interesting to know, because it tells us about the mutual buildup of these black holes and galaxies and what's going on in the inner nuclei of these merging galaxies. But to actually figure out what is happening, as I said, there are a number of different ways that you could solve the final parsec problem, but to actually understand what the mechanisms are, we need an observational handle on what the population of massive black hole binaries are. And so for example, if we could gauge observationally what the fraction of binaries at different separations are, this could tell us about the mechanisms that bring them together. And our observational handles are, as I mentioned, gravitational waves, but also electromagnetic identification of these binaries over a complementary and a wider range of parameter space. And so to kind of elaborate on this point, what I want to show you here is a plot of different binaries, essentially. So on the y-axis is the period of the binary in log years in the rest frame. And on the x-axis is the mass of the total mass of the binary in log solar masses. And what I've drawn then are lines of constant binary separation in cyan and then also just to guide the eye, the time to merger due to gravitational waves in the blue dashed lines. And here is where the two have merged. And then in these shaded regions are where different tools for finding these binaries are sensitive to. So for example, down here is where the space-based LISA will detect gravitational waves from the smaller massive black hole binaries near merger. And in the other gray shaded region is where another gravitational wave observatory, the pulsar timing arrays, will be able to detect a gravitational wave background from the most massive binaries near merger during in-spiral. And then, as I mentioned, there are electromagnetic ways to identify these binaries electromagnetically, and this is what I've shaded in this kind of teal swath. And this, so this specific tool here is I call periodic light curves. This is, you can find massive black hole binaries essentially by observing hundreds of thousands of AGN or quasars and looking for a periodic emission in their continuum light curves. So on the high period end, this is just limited by the length, how long you can look, the temporal baseline of your survey. And on the short period end, this is limited by the rarity of such objects, because the shorter their period, the less time they spend as a binary. But when I want to, and so the thing is, this kind of search tool for massive black hole binaries gives you candidates. So what I've plotted here, these black points, are existing candidates today. But to actually learn something about the population that I was mentioning before, we need to understand whether these are actually binaries and vet the candidacy. And what I'm going to talk about in this talk is a new idea for doing this, where in this orange triangle of binary parameter space, we might actually be able to directly image these binaries in the submillimeter with very long baseline interferometry. And so how exactly would we do that? So across the street, there's a team of people who are probably sitting in the audience here who are trying to image the structure of event horizon scale structure around the Milky Way black hole, the so-called Event Horizon Telescope. And so they're doing this by observing in the millimeter with baselines that are as long, well, the size of the globe, of order 10 to the 4 kilometers. And with this kind of baseline at this wavelength, you can reach down to tens or even micro-arc-second resolution, which is what the Milky Way black hole subtends on the sky at 8 kiloparsecs away. So the main point here, the main observation, is that the angular extent of the Milky Way black hole at 8 kiloparsecs is the same as the separation, 0.05 parsec separation of a massive black hole binary at a gigaparsec. So this just tells you that it might be possible to resolve that kind of separation. But the point of the calculation that Avi and I have done is to ask, are there any of these that we can actually look at? How many might there be? And so I want to quickly try and run you through that. To make that question more precise, we ask, how many are bright enough that they can be observed with something like the Event Horizon Telescope? And then how many are above a minimum separation that they're resolvable, but also below a maximum separation that we can watch their orbit in a lifetime, 10 years or something like this. And then finally, a fourth point, which could be relaxed, but we also ask that the emission region, the millimeter wavelength emission region, is small enough that it tracks both black holes rather than shrouds the entire orbit. And then to do this, we're going to do this calculation, which I want to run you through very quickly and show you some results. So this is what I was mentioning a moment ago. This is actually kind of interesting. If we ask whether this emission region is small enough to track the orbits, what we find, and I won't go through the details, but you could ask me about, is that we need to be preferentially looking at low luminosity AGN. So I just thought that was an interesting result to keep in mind. But then quickly, the way we do this calculation is simply assume that some fraction of all AGN have a massive black hole binary. And then we can say that the number of AGN per luminosity and per redshift, essentially, times a probability that AGN has a black hole in the right separation range will give you, when integrating over all luminosities and redshift, the total number of possible resolvable binaries in the sky. So this we just build from a luminosity function, which we scale to the millimeter wavelengths. And then most of the work comes into calculating this probability that your AGN has a black hole binary that is in the right separation range. And to do that, we have to come up with a simple model for how quickly the binary comes together. And so we assume a simple gas plus gravitational wave-driven model. And that will tell you at any given separation how long the binary will last there. And for example, if you know how long the AGN lives, the fraction of how long the binary lives at that separation to the total lifetime gives you a type of probability. And also, just to make the point here, we assume a model to estimate how many of these guys will be out there. But in the end, when we make observations, we'll be able to constrain these models for the decay of the binary. And then additionally, on top of this, we enforce this emission region size with models for the synchrotron emission that will create the millimeter wavelength emission. And we also constrain this fraction of AGN that have massive black hole binaries by what this probability times a number gives you in a gravitational wave background. So there are limits from the pulsar timing arrays on a gravitational wave background, which you also use to constrain this fraction of binaries. And then just to give you a kind of summary of the results so far, what I plotted here is this total number, this integral we just calculated, log of that number, versus the minimum angular resolution that you get with an instrument like the EHT, so down to 1 microarc second resolution. And then here I've just plotted different, if you go out to different redshifts, so from z 0.05 out to z of 1 or so. And at a minimum flux sensitivity in the millimeter of 10 millijanskis, which is reasonable for something like the EHT right now, although you could ask those in the audience that work at the EHT, you have a marginal ability to detect a few of these binaries with less than 5 microarc second resolution out to z of 0.5. But if you decrease your sensitivity to 1 millijansky and 0.1 millijansky, that number rises to a few hundred. And in all of these, I assume that the orbital period has to be less than 10 years. If you're also willing to wait longer, say 20 years, at the best case flux sensitivity of your instrument, you might expect to find thousands of these massive black hole binaries that you can resolve with the EHT-like instrument. And since this is the theory seminar, I'll skip this for a moment, but there's an idea of how we might go about finding targets. And I just want to say there's one or two interesting things you could do if you were to track an orbit of a binary with VLBI imaging. And the one is you can make a precise mass measurement. And that's simply because through Kepler's law, if you have the period from watching this orbit close on itself, and you assume a cosmology so you know the distance, then you're also measuring the angular size of the binary separation on the sky. And with these two together, you can make a measurement of the binary mass, which can be rather precise. And also, you might be able to make a novel measurement of the Hubble constant through a similar comparison of physical and angular distances and not assuming a cosmology. So those could be interesting things to look for in the future if you can actually make this type of imaging of a binary. So I'll just leave the summary up so we can finish on time.
Just the last bullet point there. I mean, an EHT run right now just seems like a very involved thing, right? Multiple hours in a row. There's only certain times a year you can look at particular targets. There's a lot of data processing that goes into it. But it seems like you want to go after high priority targets first, rather than doing like a blind search where there may not be anything.
Yeah, that's right.
So is that list kind of the comprehensive list, or is it just a couple of high priority?
I wouldn't say it's comprehensive, but I have talked with some of the team about these interesting targets. And some of these, for example, there already are VLBI observations of. So I think, yeah, that's the right idea, is to try and look at the high priority targets that already have observations, or you could make observations of in the near future.
Just to follow up, what's the timeline already for how long ago were those VLBI observations taken?
Which VLBI observations? Oh, the ones I just...
Yeah.
I don't know, actually, how far back they go. But 3C273 is, one of the brightest and most famous quasars. So
We are like chipping away at that 20-year.
yeah, Yeah.
Well, I have heard that if you look at AGN, in 50% of the cases you see two jets,
Mm-hmm.
which means actually that the vast parts problem is also a problem for the galaxies, because binary black holes obviously do not really merge, they just move close together, and then you get these two jets, and that's it. So I think that was surprising to me, because it means indeed there is a problem for the black holes to come together, and you can maybe use these kind of galaxies where you see the two jets as targets for your observations, because there obviously you have a binary black hole, and you might even know the distance or whatever.
Yeah, that might be could probably even do that with VLBI at longer wavelengths, because I believe those separations aren't quite as small as what I'm talking about here. So I think there's also opportunities for longer wavelength VLBI to look for larger separation black hole binaries. Yeah.
If there are no more questions, let's thank all our speakers.
Hey, Morgan. We should sit down and talk sometime. I know I've done some similar type of analysis of torques in the circumbinary.
The pink and green one is like inspired by you all's binary black holes.
Yeah, that's good stuff. Seems like we both already caught the cold too, so we can't get each other sick.
I had the flu a while ago.
Uh-oh.
Morgan, I actually was going to ask you, how's resolution affect